Have you ever turned on an irrigation zone and nothing happened? No clicks, no spray, just silence. That's where electrical troubleshooting becomes one of your most valuable skills. In this section, we'll explore how to safely identify and diagnose electrical problems in irrigation systems. You'll learn how to use a multimeter to measure voltage and resistance, interpret readings, and isolate faults in controllers, transformers, and solenoids. I'm Dr. DeBusk, and by the end of this lesson, you'll understand not only what to test, but why each measurement matters, so you can quickly find and fix issues before they turn into system failures. Before we ever pick up a meter or touch a wire, we need to talk about safety. Working around electricity, especially near water, requires complete awareness of OSHA standards, state codes, and local licensing requirements. Every technician must know what they're legally and safely allowed to do. Following these rules isn't just about compliance, it's about protecting yourself, your coworkers, and your clients. This presentation assumes you already have that foundation and are ready to apply safe, professional troubleshooting practices in the field. Effective troubleshooting isn't guesswork, it's a process. Even experienced technicians can fall into the trap of jumping to conclusions. But when you assume the cause, you risk missing related problems or covering up the real issue. Develop a step-by-step process that works for you and follow it the same way every time. That consistency is what separates an efficient technician from one who wastes time chasing false leads. Every irrigation electrical circuit follows the same path, from the power source through the controller, out to the valve and solenoid, and back again. The ultimate goal is to deliver enough voltage and current to energize the solenoid. When it isn't working correctly, that magnetic field lifts the plunger, the diaphragm opens, and water flows. If that doesn't happen, our job is to find out what in that path failed and where it happened. Troubleshooting starts at the controller because if there's no power there, nothing downstream will work. Once the controller checks out, we move to the valve circuit. Before reaching for the multimeter, start with basic visual and functioning checks. Look for obvious clues, a blank controller display, a tripped breaker, or a rain sensor that's still active. Sometimes the simplest oversight, like the water supply being off, can save hours of testing. If a customer or another technician shares details about the issue, always listen respectfully, but verify everything yourself. Never act on secondhand information unless you can confirm it firsthand. And yes, if nothing else makes sense, check if the property is possessed. A little humor goes a long way when you're elbow deep in troubleshooting. Electrical troubleshooting follows a clear 5-step process that gives you the full picture of what's happening in the system. We start by checking voltage at the controller, then trace it back to the power source and transformer, before switching to resistance readings on the valve circuit and solenoid. This sequence ensures that we identify not just where the problem appears, but why it exists. And always remember, test every station, not only the one reported. A problem in one zone can often point to something larger, like a common wire issue or a phantom voltage reading. The chart on the slide shows the relationship of how each responds to faults. Step 1 is to test the output voltage right at the controller terminal strip. Most irrigation controllers operate around 24 volts AC, but in reality, you'll see anywhere from 17 to 30 volts depending on your input voltage. Since the transformers used in controllers are 5-to-1 step-down transformers that takes the incoming line voltage of 120 volts and changes it to 24 volts, 120 volts divided by 5 is 24 volts. The voltage of a sound circuit will regularly be greater than 24 volts because the line voltage is often over 120 volts. If one station reads low, that output module might be damaged. If all of them are low or high, the problem is probably upstream at the power input or transformer. And if you ever see voltage on a station that isn't connected, don't panic. That's phantom voltage caused by electrical induction, not an actual live circuit. Next, check the input voltage going into the controller. This is the highest voltage you'll find in the system, usually between 110 and 130 volts. Knowing this number helps you predict what the output voltage should be after the transformer. If the input voltage is outside that range, the problem isn't with your irrigation components, it's a power supply issue, and that's when it's time to call a licensed electrician or the utility company. You can expect that your controller output voltage is 1/5 of your incoming voltage. Step 3 is to check the transformer output. This is where 120 volts is stepped down to about 24 volts for the irrigation system. If your readings are below 17 volts, check for loose connections or a lost leg of power. If they're above 30 volts, that usually means a partial short, time to replace the transformer. A 0 reading means the transformer has failed completely, and your next step is to install a new one before retesting. Once the controller checks out, we move to the valve circuit and use the resistance readings to interpret what's happening inside the wiring. A healthy valve circuit reads between 20 and 60 ohms. If you see OL or 1, you've got an open, a break or disconnected wire. If the number drops below 20 ohms, that's a short. Electrons are taking a shortcut somewhere. Extremely high readings mean a partial connection, usually corrosion or a poor splice limiting the flow of current. By understanding these resistance ranges, you can tell whether your issue is mechanical or electrical before digging up a single wire. Step 4 measures the resistance of the valve circuit from the controller. This single reading tells you about the entire loop, the wire, the splices, and the solenoid all at once. If resistance is normal, you're done. If it's too low, there's a short somewhere in the line. If it's too high, you likely have a partial connection, usually corrosion or a damaged splice. An OL or 1 means an open circuit, a total break in the electrical path. The final step is to isolate and test the solenoid by itself. This confirms whether the valve component is the fault or if the problem lies elsewhere in the circuit. Cut the splices, strip the wires, and measure resistance directly across the solenoid leads. If the solenoid reads below 20 ohms, it's shorted. Above 60 ohms, it's partially connected, and OL means it's open. Replace it, retest the circuit, and if the new reading returns to normal, you found your culprit. Unlike standard AC solenoids, latching solenoids are used on battery or solar-powered controllers and operate using direct current, DC. They use a small pulse of current to latch the plunger in position, up for on, down for off, and then draw no additional power. Because DC circuits are polarity sensitive, the red meter lead must be on the positive wire and the black lead on the negative. If your multimeter shows any resistance, the solenoid is good. If it shows OL or 1, that solenoid has failed and needs replacement. Testing a fuse uses the same method as testing a DC solenoid. Set your meter to ohms, connect one lead to each end, and check the display. If you see any resistance, the fuse is good. If it shows OL or 1, that fuse is blown and must be replaced. The actual number of ohms isn't important. It's the presence or absence of continuity that tells the story. No matter how experienced you are, electrical troubleshooting and irrigation systems will always bring surprises. Some conditions don't fit the standard rules, and if you don't recognize them, they can lead to misdiagnosis, wasted time, and unnecessary replacements. The 3 most common exceptions we'll look at are multiple solenoids on one circuit, high water pressure that changes current demand, and current leaks caused by poor waterproofing. Each of these behaves differently on the meter and can easily fool even a seasoned technician. One of the easiest mistakes to make in troubleshooting is misreading a low resistance as a short when in fact you're just looking at multiple solenoids on one circuit. Each solenoid gives the current another path to travel, so the total resistance drops, not rises. For example, 2 solenoids on one line may show only 10 to 25 ohms, which looks like a partial short, but it is completely normal. You can confirm this by watching the irrigation zones. If a single controller station is watering a noticeably larger area, you found your double valve circuit. Or you can measure the current. The amps will double or triple depending on how many solenoids are connected. When water pressure is too high, the solenoid has to work harder to open the valve. That extra effort shows up as an increase in inrush current, the short burst of amps needed to lift the plunger. The solenoid then settles into a lower holding current once the valve is open. For most valves, the inrush current is about twice the holding current. For example, if the holding current is 0.2 amps, the inrush current might be around 0.38 amps. When pressure climbs above 100 psi, or if the wiring is too small or too long, the available voltage may not be enough to meet that higher demand, and the valve may fail to open completely. To confirm, measure the station amperage with a clamp meter. Set it to measure AC amps, clamp around the active station wire, and use the peak function to record the highest reading as the valve activates. If that peak reading exceeds the manufacturer's specs, high water pressure or voltage drop from long or underside wire may be the root cause. Some solenoids have those values stamped on the side of the solenoid. Our last exception is current leaks, and this one's sneaky. When two unprotected splices share a wet valve box, the surrounding soil becomes a conductor. You might see two valves running at once, or a valve that stays open after its cycle ends. This happens because leaked current energizes the second solenoid just enough to keep it open, even though it shouldn't be. The fix is simple but critical. Use the best waterproof connectors available and replace any compromised splices. It's a small investment that saves hours of troubleshooting and prevents landscape damage. Phantom voltage sounds mysterious, but is actually quite simple once you understand it. It's a measurable voltage that has no current. So even though your meter shows 24 or 29 volts, there's no real energy behind it. This happens in some controllers that leak a tiny trace of voltage internally when no valve wire is attached. It's easy to mistake this for a faulty station, but the controller is perfectly fine. It just has an open circuit that shows ghost voltage without flow. To confirm phantom voltage, you just need a spare solenoid and your multimeter. With all stations powered off, clip one lead to the common terminal and one to the open station showing voltage. Then connect the solenoid across those same terminals while watching your meter. If the voltage immediately drops to zero, you've confirmed phantom voltage. There's no fault, just residual potential with no current flow. A quick tip: knowing the ohms of your other stations can also help detect multiple solenoids on one wire. If one reads about half or 1/3 of the others, that station likely shares its circuit with additional valves. Before troubleshooting a rain sensor, remember it's nothing more than a switch. When the discs inside it absorb water, they expand and open the circuit, stopping all irrigation. When they dry out, they contract and close the switch, letting the controller send power again. Depending on how the rain sensor is wired, it can stop power directly at the controller's sensor terminals or by breaking the common wire circuit. Either way, an open switch means no power reaches the valves or pump until it dries out again. Most rain sensor issues come down to wiring mistakes. One of the most common is leaving the factory jumper in place after the sensor is installed. That jumper completely bypasses the rain sensors, so the system runs even during rainfall. Another problem happens when the sensor is wired to the common wire instead of the sensor terminals. If that splice fails anywhere in the circuit, everything downstream loses power, and finding that bad splice can be a real challenge. This next warning is critical for safety and equipment protection. If a rain sensor is wired to the common and there's a pump start relay in the system, that relay's common wire must be tied in with the rain sensor's wire. If it's not, the pump can turn on while all valves remain closed, a deadhead condition that builds dangerous pressure and can damage the pump. On the flip side, if a system doesn't have a rain sensor and the jumper on the sensor terminals is missing, the controller believes it's raining and it will never start irrigation. Always double check these connections after any service work. Let's wrap up by looking at the full picture of irrigation electrical troubleshooting. Every successful technician follows a systematic process, starting with safety and power checks, then moving through the controller, transformer, and valve circuits in a consistent order. By measuring both voltage and resistance, you can quickly tell whether the problem is in the controller, the wiring, the solenoid, or even a sensor. And don't forget about exceptions like phantom voltage, multiple solenoids, or current leaks. They're easy to miss but critical to recognize. The goal is always the same: find the fault efficiently, verify the fix, and restore a safe, fully functional system.